Actually, there isn't any. It's a very simple thing that has happened here. And I'm going to go into that shirt in the back because it's a freaking awesome color. Okay. And do you see what the difference is between the top and the bottom? You don't. There's a little thing that it says here, but that does not really help you much. No. Right there.
Is this like a variation concentration gradient with respect to X, Y, and Z?
Something happened to go from fluxes to concentrations. And what is our way of getting from a flux to a concentration generally in this class? Famous dead guy. Okay. Well, okay. So literally what has happened here, and it's a little hard to see, okay, is Fick's law has been substituted into these partial differential equations. Okay. Now, this terms here, you can see that nothing really exciting happens to the accumulation term. It's a differential term, so that doesn't matter. Okay. As I go down this to cylindrical and spherical coordinates, it gets a little funky. Why does it get funky? If you've done the shell balance, for those of you that have done, we know the shell balancing limit as delta x goes to 0, first or second lecture, or whatever we had here. We did that for a slab. If you do that same analysis for a cylinder or a sphere, that's what introduces the 1 over r, del r, and all that other stuff. And you probably have this in heat transfer? I don't know, maybe? Yeah. Yes, I see a couple heads going up and down and so forth there. And you can do that as an exercise and feel really good about yourself to take a sphere, do a shell balance with little r's and del r's and all that jazz. And if you do that, that's what will happen to these here. This one here is really ugly because all of us don't really know what spherical coordinate systems are, including me. Okay, I'm like, I know R. I don't really like any of those other dimensions. Okay, and so there's this theta and the phi and all that other stuff would be true if you had, for instance, diffusion happening not just radially, but also being varying around in this direction and in the other direction that's the orthogonal coordinate system of a sphere. Okay. And you can kind of imagine the chances of you ever having to deal with that problem in this class are about 0. Okay? But if you needed to, okay, so this is just saving you the mistakes of coming up with the shell balance to be able to deal with flux as it varies in spherical and cylindrical coordinate systems in all directions. For those of you that like the subtractive way to engineering, and the way this was actually taught to me a gazillion years ago, you can always take this equation and then just get rid of the stuff that you don't like. And so if I have diffusion, radial diffusion in a sphere, and it doesn't vary around the sphere this way, then I can get rid of that phi thing, okay? Because that's variation, the del phi of flux of whatever this crap is 0. Because it's not varying as I go around. And then there's the other one that's like this, right? From the other coordinate goes from here and then down. Well, if it's not varying that way either, then I can take that del whatever thingy here, okay? And that goes 0 too. This is the subtractive way of dealing with this problem. And all you end up with is that one. And that's the one I hope to go through here today quick, is solving this analytical problem for diffusion in a sphere. And then all of you can go back and play with a cylinder as either homework can be homework or it can be assigned. Okay? Either one of those. So then you get down to here. Remember, Fick's law, the way we have a tendency to write it, is kind of like for slab. Okay, and so this one here makes the substitution of Fick's law into this where now everything are gradients in concentration, where I've also taken into account the definition for Fick's law in curved systems of a sphere and a cylinder as well. Okay. So you all know what this thing is, right? Okay, so let's actually then take a look at this problem as if I was going to try to get this line, the sphere, and the actual mathematics of that in this particular problem. So if we started from here, and we wanted to go after, if you will, this particular problem of radial mass transfer, we have among this, we know that there's no reaction, right? Not a reacting system. There is at the boundary, but that's not what we're analyzing. We're analyzing diffusion in the area in which there is no reaction, and so that's not part of the problem. It's a pseudo-steady state one, so we can get rid of that. There's no variation in the sphere going in the phi in the direction, and so there you go. That's what I need to solve as my equation for that. And it looks pretty easy, okay? Now, should we do it based on flux, or should we do it based on... It doesn't really matter. We'll do it with Fick's law. So I'm going to actually take this thing, and let's see, I'm going to take this on up. And there it is. This equal to 0 is the actual equation that I'm going to be solving. 2, 2, 3. Doesn't look like it's too bad. Okay, so let's go ahead and find the diffusion coefficient. We have 1 over r squared. Del r. We can now change that to a differential, right? It's written as a partial differential because there's like multiple of them, and you can't have. If there's only one derivative, partial derivative is equal to a quote unquote real derivative. So here we have CDR, and then we'll set that equal to 0. To solve that mathematically, I can get used to what I'm working with here. Well, I'm kind of a bit wonky. That means, sort of by definition, if I take that to the other side, still 0. Take the r's to the other side, they get out of my way, and so I end up with, did I actually not write this correctly here? 1 over r delta r, I missed an r squared. R squared. Okay, I'll sneak that one in there. Yeah.
How did you assume steady state?
Because it is a steady state diffusion problem. It says, right from there, of the pseudo steady state diffusion problem. Everything that we're doing so far in this class has been. That confirms what I'm going to do in my next lecture because I've been trying to avoid that. Okay. But I don't see how, because it's not in the regular course to deal with unsteady state necessarily. But why wouldn't we? I mean, it's right there. It's just one more thing, a little bit of mathematics. How do you solve that problem? You right? Well, including this term. It's right here. Yeah, so you include this term, but how do you solve this problem? Separation variables. So it is a partial differential equation. They have to remain deltas, not d's. And then you do separation of variables and all that fun stuff that you had in Math 251. Okay, so let's go ahead and solve this particular problem. Okay, so what this really means then is that, okay, I left my derivative. Yeah. I know I left it out. Where is it? I know it is. It's right here. Ah, okay. 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 So the term that I actually have to do here is the diffusion coefficient AB. Let me actually say 1 over r squared. And then we have delta r, which will be ddr, and r squared dc dr. Did I get that right this time?
Yes.
And that's equal to 0. What are our boundary conditions? We're way to the back. One with a sporting lot of hair. When you meet my brother, yeah, I just actually even noticed. My brother, his hair is actually lower than his ass. Okay, I didn't even notice that until last night. The other guy cut 20 years. Say that again, I'm sorry. In this case, it would be at R equal that fractional R thing, right? Okay, well that fraction is going to be like 0.01 or something. It's just something to prevent us from dealing with the zero condition, which is going to blow up in our face. Okay. And at that particular condition, CA equals 0. That's one of our boundary conditions. The other one will be at R equal R. What is it equal to? CA equals CA 0. Okay. Two boundary conditions, second order differential equation. This should be a piece of cake, right? In this particular case, I look at this and I can immediately see that DDR, or D, if you will, R squared, DCDR, is equal to 0, right? Which means that R squared DCDR is going to be equal to K1. Oh, I'm sorry. Yeah, R squared. That's just by definition of a derivative. It's a derivative constant. Which means then we can go ahead and you can tackle this carefully to get it. And if you, yes.
Where'd you get the first one is equal to 0? Like the second one?
The second one here?
Yes.
I divided by dp in this because that goes away. I multiplied times R squared to make it go away. And then I took the dr onto that side, and then all I end up with is d equals 0.
Okay.
Okay? Yeah. Don't hesitate to ask little questions, because I almost just simply wrote it as equal to a constant. And then left you figure out so what do you do here? Then you have now dc equals, we have k1 over r squared. You can see why I was trying to avoid the boundary condition of r equals 0. Okay. dr. There's systematic ways to deal with boundary conditions, and there's intuitive ways. I happen to know if I do a definite integral first, and I'm working with the boundary conditions as I are, I can get my k1 easily. You have to just keep track of stuff. You can do it as an indefinite integral, and then integrate your whole way down, get your two constants, then plug crap in, get two simultaneous differential or algebraic equations, and solve for C1 or K1 and K2. Okay. That's all been taught to you. Taught to you more than my entire education. Okay. So, with that in mind, I'm just going to integrate this over something that makes sense. I know that if I integrate this thing from 0 to CA0, that will be an integral in R from where to where? And I'll just here. That little fractional thingy, right? So that'll be F del to del. And how am I doing? Oh, I'm doing okay on time. I just see people failing. If I don't need to do the rest, it's right there. Okay. Yeah, no, I'll walk you through the rest of this. Okay. So from this, I should be able to solve. Keep in mind what you're doing. This is where the calculus gets you. I did a definite integral, which means I can immediately solve for my constant of integration. What happens is people get a little confused about what they're doing. They do a partial from a boundary condition to a non, like from CA0 to R, you know, and then they get, am I really solving for K1 or not? You need to get that stuff clear in your head mathematically, because that was what calculus is about. So I'm solving for K1 based on a definite integral. Keep in mind I hate math. But I found, no, I actually don't. Okay. It's logical, just sometimes kicks my wrong. So, can you do this? I get CA0, right? CA minus 0. What do I get on this other side? You have to remember that little thing of the integral of R to the minus 2 dr which is going to be equal to minus 1 r to the add 1 kind of thing. And so that will be r to the minus 1 plus a constant, right? C1, that's, you all remember that thing? Okay. This will be equal to K1, which is a constant, and that integral that you'll have there, which will be minus 1 over r evaluated at from del to frickin' del. Okay, and that will be equal to K1 times minus 1 over del plus 1 over f del, which I don't like because I know if I put an f and an f there, I'll get 1 minus f over f del. Okay. I hate to penalize people for doing terrible things that I make mistakes all at the same time. And I know there's this tendency for people to think like if I start to reduce anything I do, I might make a mistake and I'm going to get a lot of my credit taken off. That's kind of not fair to those who actually make an effort to put it in a form that makes sense so you can actually see the logic later. And so if you make a little algebra mistake or something like that by trying to put it in a logical form, I will do my best to not penalize you, okay? Rather than you leaving it into a bunch of crap, okay, which I'm supposed to substitute back in and figure out if you actually have this thing right. I don't. Okay. Solve for K1. That's easy. Okay, K1 equals, anyone? CA0 friggin' del over 1 minus friggin'. Okay. So we have our value of K1, but we don't have an equation. What are we after here? Concentration as a function of radius, right? You're not going to get that from a definite integral because there's no r left over because you plugged in and got rid of them. So then you have to do the indefinite integral to get that indefinite integral. And so we have to go back up here. Oh, by the way, for those of you that were wondering about the whole curvature thing, it's right here, right? Because what you see is that that means that you have dc dr, that gradient that you were drawing in your picture, is going to be equal to some constant over r squared. So clearly, as you decrease the value of r, the only way that you can have that be true is that it implies that you must increase dc dr. Okay, I'm just. It's always nice to do that little brainy check of making sense, yeah.
For that f, what does that physically mean? Because
I'm sorry, the what?
so for you took the f out when you simplified it. So you had f del.
No, I just multiplied times the top. My basic pointer. Okay. The 1 over del, I put an f on the top and the bottom, and then I made an f.
Yeah.
And I just algebraically, it's the fraction. It's like, this is one thing, and this is f times that one thing.
So what's the difference between f and f del?
It's f times del. Yeah, it's a fraction times the del, because by defining things in these ways, you often get an equation that's much easier to understand rather than just defining it as some other thing. I know what f is. F is going to be like 0.01. It's a small fractional number, no units. It's f times del. Okay, and then otherwise, if I just arbitrarily define things, they don't reduce in ways that are nice to look at. That's the only reason I did that. For the sake of the 3 minutes that I have left here, okay, I have to go back to this thing and actually do the definite integral, which would be dc is going to be equal to k1 over r squared dr. And I'm going to want to go, well, I'll do an indefinite so that I end up with c sub a equals, in this case, k1 minus 1 over r plus k2. to the indefinite interval now. Now I have an R-dependent thingamajiggy, right? And then I can sub in the other boundary condition. Sub in the other boundary condition to find K2. Okay. As simple as this looks, I realize how easy it is for you to be like train wreck on these things. It's like, I know this is so easy, and then all of a sudden, it doesn't happen, and you get all frustrated. Okay. And so now I need to use the second boundary condition. Well, I already used basically that one. And so with this one here, I'm going to go ahead and plug in the other one, and that is at, well, I'll make it into, did I do it the same way? CA0 is going to be where R is equal to big R, so that'll be equal to K1 minus, well, I'm going to be K2 over here, minus 1 over R. And so I can find the answer here by dividing through and get CA0 over K1 plus, I'm going to make a mistake. Equals K2. Did I do that right? Yeah, looks like I did. Okay. So now all I need to do is, to get my answer, I need to plug in K1 and K2. Right. But since K2 is already a function of K1, you're much better off to plug it in before you try to solve all of that. Okay. And so I'm just going to take my answer here, which is this one here. This one here is going to go on down. And I'm going to go CA is going to be equal to K1, K2 minus 1 over R. And I'm going to go ahead and plug in my K2 and get K1 times CA0 over K1 plus 1 over R. That's my K2 minus 1 over R. And I multiply through, and I'm going to get something that I'm going to be happy about because it's going to be CA0 right? Here, plus, and then I'm going to have a K1 times.
You can't see that.
Oh, sorry. Then it'll be 1 over R minus 1 over R. I'm sure there's a negative sign somewhere. And then I'm going to take my K1, which is up here, right? Okay, K1 is K2. And the K1 is going to be CA0 plus K1, which is CA0 L over 1 minus F, 1 minus F times 1 over R over R. I feel like I lost an R somewhere. It's looking good. You get the idea. Okay. What's the point? The point of this was to end up with an equation that would give you concentration as a function of radius based on two boundary conditions that are known. Okay? And you can go through this and you find that the functional dependence is basically 1 over R. If you do this same mathematics for the other case, which I recommend that you do at home, okay, i.e. cylindrical coordinate systems, okay, you end up with even more mathematical fun, okay, because it all ends up with logarithms and all that kind of fun stuff as well. And it makes sense, right? Logarithm is somewhere between 1 over R and independent. Okay? So, goal of today was understanding how to deal with curvature. So it's not always the Jello problem, and when you have curvature, You have to play a lot more with the actual mathematics to make the flux, and the mass balance actually balance out. Okay.
If you write anything on your computer, you need to get grammar.
I read English.
I'm just leaving it as well.
I talked to 3 companies, I got 3 interviews.
Hi. Those extras? Okay, I'll take them. I don't have to do them. Thank you.
Is that your
I'm meeting with him after class. Thank you.
From Johnson & Johnson. What is that? Did you just record that lecture?
So I tried, and so it recorded the first 15 minutes, and then it stopped doing things, and then I tried to record for 10 minutes, and then it's actually still recording, so you can still hear me talking. So I am going to stop this.